we'll do a short little one here where we talk a little bit more about this issue of the boundaries. Because if I now want to think, because this is a common thing that happens. It happened, you did it in waves, and you did it when you did the square wave potential in quantum mechanics. What is, for instance, if I have an infinite potential from 0 to A, what is the boundary condition on the wave function at 0 and A? Has to be 0. Infinite square well. I believe you all did that in 61A. Think back. Okay, I can ask it another way. Suppose I have a wave on a string and the ends are fixed. What's the boundary condition on the wave? 0. So it's a common situation in physics where we have the 0 boundary condition on the endpoints. Now notice, being 0 on the endpoints is also what? How else would you just, a function that's f of 0 equals f of a that just happens to equal 0, it's not only 0 at the boundary, it also is periodic at the boundaries. So now let's think about our sines and cosines for a second. If I'm going to go from 0 to some position A, and I want to draw the sort of lowest mode periodic. Let's say I'm thinking now of it as periodic, which we've just been doing. What am I going to draw for a sine and a cosine? So actually, why don't you do this on your paper? So you draw for me, going from 0 to A, the lowest mode, the lowest sine and cosine. Draw one picture for each that you can fit, assuming this thing is fully periodic from 0 to A. Right, what sine and what cosine do you draw? I'll give you a hint. The sine starts at 0, the cosine starts at 1. So I'd ask you to hold up your picture now, because they're probably all too small for me to see. This is where what I would love, as a little aside, is that y'all had your iPad type device. You drew it on your device, and then you sent it to me, and I displayed them all on the screen, and we could see all the pictures. Wouldn't that be awesome? That would be pretty awesome. I mean, how many of you been at Disneyland in the Innovations where they have the tables where you can slide pictures from table to table? That's what I want. I want you all to have your device, and then you just, we have 20 screens around the room, and we're putting them. Man, that would make it so much fun. I don't know if it impacts learning or not, but it would be cool. So what are we drawing for a sine wave? Okay, is that fully periodic if I draw one lobe? No, it's not. It's only half, right? The sine wave that's periodic is that, right? It is sine 2 pi x over a. What's the cosine that's periodic? It's easier to realize it has to be that, right? And it's cosine 2 pi x over a, which is exactly what we said. If I stick a little n in here, right? That's our basis vectors for periodic functions from 0 to a. Now, if instead what I do is ask you to draw the functions that go to 0 from 0 to a, what do you start with now? First of all, is cosine allowed at all? No. No. Why is cosine not allowed? Because it's 1 at 0. And so I have to draw sines, and what's the first sine I draw that's 0 between 0 and a? Now I draw the half, and I'm drawing sine pi x over a. This is not a full period of the sine function, because notice the slope has not come back. Right? That is a full period. So that's drawing the first function I can that's periodic from 0 to a. This is drawing the first function I can that's 0 at 0 and a. But it's not fully periodic. That's not the period of the sine function. That is not one full period. That is half a period. but it is 0 at both ends. So notice this is, and then I could stick an n in and get all my basis vectors. So if you look back at the infinite square well potential for quantum mechanics, which you did do in 61A, you will see that your eigenfunctions were sine pi nx over a, not sine 2 pi. And you didn't have any cosines, because you were worried about functions that were 0 at the boundaries, not periodic functions. You weren't worried about the more general case. Now, let's see how, first of all, any questions on that? And this is the same if I pick a rope and fix it at both ends, or a pipe with sound in it, I fix it at both ends. This is not a quantum mechanics thing, this is a wave thing. This is a linear vector space boundary condition thing. So now, let's imagine this is my function. So it's a triangle wave going from 0 to 1. So this is my 0 to a. It's 0 at 1, it's 0 at 0. Now I want to do a Fourier series for it. I can think of this as a periodic function, or I can think of this as a function that's 0 at the boundaries. Now, in this case, the first thing I'll do is, what just happened there? Shoot, I don't have fn sign defined. Darn it. Well, I'm not actually going to execute the rest of the things. I'll put fn sign in. I had defined our basis functions for us in an earlier version of it and clearly cut it out of this file before putting it here. So instead of taking the time to type it, notice we can get cosine terms and sine terms, and then we can sum them together, and we can plot it. And I can apparently not type the word notice very well. But if I plot it, notice what's happening down here at 0 and 1. I'm assuming periodic. I'm getting basically a triangle wave, but it's not going to 0. It's being periodic, but the fact that I had to use some cosines to get the shape, because I'm using sine 2 pi nx, there's always going to be some non-zero contribution here. They try hard to cancel out the different cosines, but they don't do it exactly. If I change my basis function to sine n pi x, and now I integrate, I get the red plot. And notice it matches as it has to, right? No matter how many terms I have, I at least get my boundaries right. I've now made the boundaries correct, and then if I compare my different approximations, so one of the things, this from a Mathematica point of view, I wanted to show you is the show command. If you've done a bunch of plots and you want to look at them together, show allows you to plot them together. Show also allows you to put graphics on plots, put graphics together, as you draw stuff. And now I have all three of them here. You can see, at the top they have slightly different approximations. The periodic function is actually doing a little bit better to get the point. The cosines help make that a little bit sharper. But down here, if you look real closely, the blue is missing and the red doesn't. So depending what your goal is with your series approximation, what you're trying to achieve, what you're trying to match, whether you think of this as a periodic function or whether you think of this as a function f of 0 equals f of a equals 0 will determine which basis set you use. And those two basis sets do a different job of approximating the function in different places. So again, understanding these series expansions as an expansion in a basis in a linear vector space is an incredibly powerful idea for getting at the physics you want to get at. If the key physics in the problem is the boundary condition, then you're going to use the sign n pi x. If for some reason you're looking at something in the middle and you don't care about what's happening at the boundaries, you might be better off with the the cosines and sines in the 2 pi nx, or in that case using e to the I. And from a physics point of view, From a purely physics point of view, if I'm in free space, what was the wave function of my particle based on? Basically, in free space, what are the wave functions of free particles? Anyone remember from 61A? Yeah, I know. Darn it. That was like a whole 7 weeks ago by now. E to the ikx. Those are your free space particles. If I'm in an infinite potential, then I have to worry about things being sine n pi x. Those are my energy eigenstates because they match the boundaries and work out. But notice, if I'm in the middle here and those things are far enough away, I'm not going to have to be worrying about the boundaries anymore, and then using e to the ikx's are perfectly fine and can give me a good approximation. So that's kind of the physics way to think about what went on with those two formal maths series. Make some sense? No sense? Little sense?